Hello everyone, this is Kaveh coming to you from Hawaii. This is our second Lisp lesson, common Lisp lesson. So I hope you enjoyed the first one. Um, to start off with, let's address a few of the comments that were made on the previous lesson. So I did receive some feedback. I'm just going to kind of go through it. One key binding in Emacs that's useful is Control-C, Control-K. That evaluates the entire buffer. I think in my last lesson, I selected the buffer and then evaluated the region. Someone kindly pointed out that there's a key binding that evaluates the entire buffer automatically. Control-C, Control-J is another useful key binding that evaluates the expression and then sends the result to the REPL. I think what I did last time was, let's go back to the previous lesson. When I created a point P, when I hit Control-C, Control-C to compile the type of P, it doesn't echo the result in the REPL. But if I hit Control-C, Control-J, it does put the result in the REPL. So that's useful, another useful hint. So I'm learning some new things as well here. Same thing, obviously, with the class and so on. So that's another useful comment on YouTube. Thank you so much. Oops. Sorry, getting lost in my buffers here. Let's go back to lesson 2. Somebody else also pointed out that in my code, when I had a lambda, we don't actually need the hash quote before the lambda expression, because the lambda expression itself evaluates to a function. So this, it's an optional thing that you can have if you want to, it works. But if we hit Control-CC here, we'll see it prints out the result, so it works without the function identifier. However, if I'm using a symbol, like the odd p example that we did, I have to have the function identifier. Otherwise, it'll say odd p is an undefined symbol. So in this case, I do need it. But if I have an actual lambda expression, I don't need that. And that's an oversight on my part. We had a comment from a very experienced common Lisp programmer who used to actually work, I believe, at Symbolics. And he pointed out that I could have used the prog1 construct when in the with redraw macro. So to refresh our memories, what I did for the with redraw macro was I bound the result to the variable result by doing a prog_n. A prog_n evaluates a series of expressions and returns the last one. And then I did the redraw, and then I returned the result. So prog1 is a construct that basically returns the first thing that is in the list of expressions. So here, it'll return the first expression in the body. So if I, let's call it with redraw 1, so we don't clobber old stuff. So basically, if I define this, and then I do with, I should use Control-C, Control-J, which we learned. So if you see, we have with redraw 1 has two expressions in there, adds these two numbers and adds these two numbers, and it returns the result of the first expression, 3. And that's not what we want. We want it to return the result of the last expression before it does a redraw. So the solution to that is to wrap the body in a prog_n. So this prog_n returns the last expression in the body. Prog1 returns the first expression it encounters, so it returns the last expression in the body, and then it does the redraw. So if we now try it again, we see that it's doing the right thing. and it's returning 7. So this is a good segue into the next and final comment that we had. So Common Lisp is a very large language. The ANSI standard, I think, is over 1,000 pages long. And it's one of the biggest standards of a computer language, I think, ever. And it has a long history, and it had been in use for about 20 years before it was started to be standardized. So there's a lot of stuff that's in there. And there are many ways of doing things in Common Lisp. Unlike a language like Python, where there's pretty much set ways of doing everything, and that makes it familiar to everybody who knows how to use Python, Common Lisp has many, many ways of doing things. And so basically, this expression here is another way of doing what we did before with an explicit result. It depends on your style and how familiar you are with the Common Lisp idiosyncrasies and features. And the features are all there because at some point somebody found them useful. So that's one of the things you realize when you start using Common Lisp is how much stuff is in there that you find useful. And it's amazing what they thought of when they were coming up with the language and the standard for the language. So this language was really designed by people who knew what they were doing, and they worked hard on coming up with a good standard. So prog1 is another one of those constructs which basically will evaluate lists of expressions, and just happens to return the very first one. The final comment that I got was, why am I not doing things in a more SICP way? SICP is a book, Structure and Interpretation of Computer Programs, written by Jerry Sussman and Hal Abelson. I was actually at MIT back in the day, and I took that course from them. And it's a programming course which teaches Scheme and teaches the principles of programming in a very interesting and elegant way using Scheme as the vehicle. And in there, they basically, using lists and first-class functions, define their own effectively objects and method dispatches and so on, and message passing and what have you, to illustrate those concepts with minimal syntactic overhead, syntactic sugar. So the comment that I got on one of my the YouTube video was, why am I not using that method and why am I using object-oriented mechanisms? And the answer to that is basically SICP is very good for teaching the basic principles of programming, but if you want to develop something that's more industrial in scale, then you need a proper object system with all the facilities that it provides and all the features that it provides. And if I had to re-implement CLOS in basic Common Lisp or even basic Scheme, that would be a lot of work, and it's not necessary. So Common Lisp is sometimes bundled in with other Lisps, and they say it's just good for functional programming and that's it. It's not necessarily the case. It's a general purpose program that can do many paradigms of programming. You can do OO programming, declarative programming, you can do logic programming in Common Lisp. So it's, there's a reason why it's called a programmable programming language. So you have all of these features that you have at your disposal. And so I've chosen to basically use all of the features that Common Lisp provides, and CLOS is probably one of the best object systems and most flexible, powerful object systems out there, and I'm going to use it for these lessons. All right, thank you for bearing with me while we went over the comments from the last lesson. Let's carry on now for a brief lesson today. So I'm just going to bring the print object from last time so we have that and it's useful for us. So today we're just going to generate a few shapes mathematically. We defined our class shape last time. Here, which basically contain a list of points. So now we're going to define functions that are going to generate those lists of points and make us particular kinds of shapes. The first shape we're going to look at is basically a circle. So here we're going to have a function just called make circle shape. And it takes a diameter and an optional number of points. It's the first time we've seen optional arguments. And basically, the optional arguments, you have an optional keyword, and then you give it the variable name, argument name, and the default value. So if the number of points is not specified, it's going to be default to 64. Otherwise, I can specify it. So we have our radius, which is half our diameter, and then we have the step size in angle in radians, which is basically 360 divided by number of points. We make the shape here, and then basically we add the points to it down here one by one. So we loop through the number of points and compute the angle for that point, and then we pass the sine and cosine of the angle to calculate the x and the y coordinates, scaling it by the radius. And then finally, when that's all done, we return the shape that we created up here so that we have the polygon shape being returned. So if we try that here, we have a circle that we've created with 64 points. Now, one of the things we're going to encounter a lot is the need to add shapes to the scene, redraw it, but also to clear the scene before we add the new shape. So we're going to create a new macro called with clear and redraw. And what that does is basically does a clear first, clears all the shapes in the scene, and then essentially does what the with redraw macro did. So it stores the results for us, does the redraw, and returns the results. And based on the feedback that we got from the previous lesson, there is another way you can do this without specifying an explicit result variable that you can temporarily store things in. And you can do it this way as well, which is basically just do the prog1 of the prog_n. So prog_n again returns the last expression value in the body. Prog1 returns the first expression value it encounters, so it'll return that value after it does the rest of the list, which is the redraw. So these two are equivalent. It's a stylistic choice. This one is perhaps a little more explicit and clear as to exactly what's going on. If you look at it the first time, you can understand what's going on. This one requires a little bit more knowledge of Lisp, but it's a little bit more brief and terse and requires that you understand how prog1 works. So if we now use the with clear and redraw and add 4 shapes to the scene, we're going to make different shapes with different radii and different numbers of points. So these are the optional variables, number of points that I'm specifying here. So you can see that the number of points gets smaller, and by the time you get to the middle, you can see it's basically an octagon, and you can see the facets of it. If you want to see what the macro expansion for this is, so we have a prog_n, which combines everything together. It does the clear shapes on the scene, and then it lets the result be the prog_n of our 4 expressions, which happens to be whatever add shape scene of make circle shape this last expression returns, which is actually the circle shape. And then it does the redraw and then returns the result. So again, a very useful macro that we're going to be able to use in our code. So here we have, if we want to, we can basically then loop through all the scenes, all the shapes in the scene, and randomize the points. This is the exact same thing we did for the squares in lesson 1. So if I do this, you can see that the points on the circles get perturbed, and I can keep repeating it, and they get increasingly perturbed until after a while you can't really tell what they are. So another thing we can do with macros is basically, if we can generate a circle, we can generate any regular polyhedron. So for example, we saw that if we do a circle of 8, it's an octagon. So one thing we can do is, if we want to have explicit functions that basically say make triangle, make pentagon, make hexagon, etc., etc., we don't want to define those by hand. We could, but we can just write a macro that does that for us. So what we do here is basically we define a macro called def polygon shape, takes a name to use in the function name that's going to generate, and a number, which is number of points that's going to generate for us. So this is the first macro I think we've seen that actually defines a function. So this is one of the useful things, powerful things about macros, is they can define functions for you that you can then use as regular functions. So simcat just concatenates some symbols together. You don't have to worry about the expression. If you're really curious to see how it works, you can go into the beginning of lesson 1 of the util section, have a look at that. So it'll make a name called make-name-shape. It takes one argument, which is the size, and then it makes the circle shape of that size, and we pass in the number from the argument that we gave it. So if we basically, these have already been evaluated, but if we evaluate these, let's actually show what the expansion looks like. So this is the code for creating the function make pentagon shape. So as you can see, it's pretty straightforward. It just creates a function called make pentagon shape of size, and it makes the circle shape of that size with 5 points. Same with diamond, hexagon, heptagon, octagon, and equilateral triangle. So if I do that, and I gave them all the same exact radius, you can see that you get this kind of psychedelic looking thing where you have a triangle in the middle, and then you have a quad, and then you have a pentagon, hexagon, heptagon, octagon, etc. And they all have the same radius, so they're all basically on the same circle. If you do the same thing, but we give it different radii, so they're clearer and not overlapping so much, you can see that we've got these shapes now that have different number of points. But it's all basically still calling the make circle shape with a different number of points. And if we do our randomized thing again, we can basically take the points and randomize them as we like. Another mathematical shape we can define is a sine curve. So same kind of thing. It takes an optional number of segments, which is a number of points basically, but since this is an open shape, we deal in terms of segments, not points. It takes an angle delta, which is similar to basically the circle one, and then you make the polygon shape, and we pass it, the flag is closed shape is nil, because sine curve is not a closed shape. And then we loop through the angle, and we add the points to the shape, and the points basically a value between 0 and 1 for the x value, and then the sine of the angle for the y value. So if we look at this and we see what it does, we can see that it's giving us a sine curve. Remember, our coordinates go from -1 to +1 in the window. So this is going from 0 to 1 to -1 back to 0 as it goes from 0 to 1 in x. So it's a sine curve. And then again, in the kind of philosophy of letting macros do work for us, this might be getting a little bit hairy, but don't worry about the details. It's just the idea that I can create trigonometric curve shapes automatically by giving it a function to execute. So the thing is, this does the make function name curve shape, which is the same thing we did with the circles and the hexagons and so on. But we also give it a function to execute, so that down here, the y value is going to be the function of the angle, which in our sine curve case was the sine of the angle. And we're basically going to use this to create two functions, which we'll execute here, which is a function called make sine curve shape, and a function called make cosine curve shape. And if I create those two curves and put them in the scene, you can now see we have a sine curve, and then we have a cosine curve, which goes from 1 down to -1, back to +1. And if we want to see what the macro expansion of those expressions is, so this is a function that's being generated for us now. and we gave it the sine curve name to put in there, and then it executes the sine function to get the y value. If we do the cosine version of it, it's identical. It's identical, except that it's cosine in the name and cos instead of sine in the computation of the point xy coordinates. So this is like to show you how macros can be very useful. If you have things that are similar and follow a certain template, have a lot of boilerplate, then macros are really very powerful to basically generate stuff for you. And so you don't have to type it in yourself, get it wrong, make mistakes, make typos, have to maintain 6 copies of very similar functions, and so forth. Some people say that, first rule of macros is don't use macros. And you do need to be aware of why you're using them. But anytime you actually want to generate code, that's when you want to use macros. To finish up with, we'll do another little variation of our circle shape, and we'll have it do a spiral for us. So this is our code for the circle. And to make a spiral instead of a circle, the only thing we need to do is basically modify the radius value for each of the points. So as we're sweeping across the angles, we're going to modify the radius instead of having it just be a constant. So evaluate this. And then also we have a number of loops, because a circle would have like one loop, 0 over 360, or 0 to pi if you're in radians. But we can change that number for a spiral. So if we want to go a little longer, sorry, this is the diameter is 1.5, it's one loop. So this is a spiral of one loop. You can see it's starting, it starts at radius 0, but it's starting at angle 0, and then finishing up at angle 360. So if we give it the number of points and the number of loops, which were optional arguments, so they have default values, which is what got used in the first time in this first expression. But now here, it's doing 2 loops and 256 points to keep it smooth. And then you can, continue that and go more loops and more points and what have you to get more interesting shapes. So the idea here was to show you a little bit of use of macros and how we can basically generate mathematical shapes and then just put those results into our shape class, or polygon shape class, and then render them. So thank you very much. This was lesson 2, and we will have lesson 3 soon. So again, if you have any comments, please feel free to comment on the YouTube comments section, and I will address your comments if I can in the next lesson or 2. And I also post these on Reddit in the Lisp group subreddit if you want to see them there. All right, thank you everyone. Goodbye.